So what we're going to do today is we're going to continue lesson 3, and we are going to continue with the similar polygons. So we have a little bit more on the polygon stuff here, and that is concave polygons and convex polygons. Okay, so I'll draw a picture of each one first, and then you can kind of tell the difference between the two. The first one is concave. I think the easiest one to look at is this pentagon here. That's a pentagon. That is concave. Here is a convex pentagon. That's a little bad, but okay, a little better. So this is concave and convex. What do you think the difference is? Annabelle.
In the concave one, the point is going in.
Yeah, the corner is pointing in, right? Or vertice is in the inside or points in. And on convex, all of the vertices point outward. So maybe, we can write that. So all vertices point outward. I ran out of space there. So all vertices point outward. For concave, we can say a vertice or more. A vertice points inward. Okay, so we can say that. There's also a longer version. We also can say that any 2 points on the interior of a convex polygon can be connected with a straight line that cuts a side of the polygon. The vice versa of that can work for convex polygons, which means that no 2 points can be connected on the interior of a convex polygon. Therefore, it would be convex. Okay? So I'm going to show you this on that concave polygon. If I change my colors here, and I write a point here, way up there, and a point down here. I know it's kind of hard to see on the screen. But if I connect those 2 points, where does the line happen to go? It cuts a side, or it goes on the outside of the polygon before it comes back in, right? So therefore, that is not convex, it's concave. Okay, correction. This is any 2 points on the interior of a concave polygon can be connected to a straight line that cuts the side, okay? Versus a convex would be it does not leave the inside, it always stays on the inside. Next, when we talk about polygons, as in the header of this is similar polygons, we have to talk about what does it mean to be similar. Does anybody know what happens to me similar? If I'm similar, like sometimes if you know some guys it's a little easier, I think. Sometimes you can say a guy is similar to his dad. And what do we mean by that? They like look like each other, right? Just maybe a smaller version. If you think about it, it's kind of interesting when you have parent-teacher conferences. You kind of know whose parents are whose. But similar means that you have the same shape. Everything's the same except for the size. Okay? As in angle-wise. And so what they say, it's a magnification or reduction of another shape. So it means I can make it larger or I can make it smaller. Okay? You guys get the idea of what that could look like. This triangle and this triangle are similar. We'll assume that, we have both 90-degree triangles, and as long as I go and tell you, hey, those two other angles are the same. If I know two angles in a triangle are the same, what can that apply about the third? It has to be the same as well, because they all add up to 180. That's something that's really kind of nice and unique about triangles, is that if you know two angles, you actually know all three. Okay, now, saying that it's just a magnification or reduction of another shape, that magnification or reduction is called the scale factor. And then that is what I'm going to call the ratio between corresponding sides of similar figures. So, what we can say is that there's a scale factor between those two triangles sitting there, that the larger one, or the smaller one, is 3/4 the size of the larger one. That could be a scale factor. So that means that this side to this side is a 3/4 reduction. Now we could flip that, right? That's going in this direction. What happens if I go in that direction? I can also say that there's a scale factor there that just flips it to say that the larger one is 4/3 the smaller version. The scale factor between two similar objects or figures never changes. It's always going to be the same. So once you establish what it is, you can find other sides, as long as you're given one of them, and the ratio, you can find all three sides. Okay? And again, it matters which way you're going, from the large to the small or small to the large, that ratio can be flipped. And again, we're going to set up a proportion to make that work. So, for two polygons to be similar, the measures of blank angles must be equal. Well, this one's kind of big. This one, you have to have, just like above where it says the ratio between corresponding sides of similar figures would have that scale factor, the measures of blank angles must be equal, and those are corresponding angles must be equal. Look at our two triangles. They both have, in the same position, a 90-degree angle, and then whatever that other angle is, we said, hey, those ones down in the bottom right are also the same, which means the top one's the same. And then the length of corresponding sides must be, if you happen to have corresponding sides or corresponding angles which correspond with sides, they must be proportional, or aka have that scale factor. In our triangles, 3/4 or 4/3. Matters which way, again, you're looking at them. Similar triangles is the next one. Similar triangles, we can say, have, change the color here, have angles that are the same, so corresponding angles, all three of them, okay? So their sides are proportional. I don't have to write that. The sides are proportional. That's the definition of similar. They just happen to be triangles. We got a little star there. It says that when two triangles in one triangle have the same measures as two angles in another triangle, the triangles are similar because the other angles must also have the equal measure. what this is really setting up is that if you know AA, it implies A. And when we're talking about triangles, AAA is a very important thing. It basically sets up the fact that you know they're going to be similar. Now, what does AA mean and AAA mean? Angle, angle. So 2 angles the same implies all 3 angles the same. Because again, we talked about the fact that they add up to 180. And if you know 2 of them, then you have to know the third one. And if 2 are the same, that means the third angle is always going to be the same as each other as well. So this sets up similarity. That sets up similarity. Now, there's a step further than this, that if you wanted to say things are congruent things are similar. But similarity does not mean they're congruent. Take a look at our 2 triangles there. If I go and I say, hey, this angle and that angle are the same, and I choose to tell you that this angle and this angle are the same, what can we apply then? That our third angle would have to be the same as well. That means they are similar objects. That means they have a scale factor between the 2. I'll put some values on there to show you that. That means all 3 angles, they're similar. Are they congruent?
No.
To be congruent, they have to be exactly the same. Guess what? If they are congruent, that would actually mean that they have a scale factor of 1. They have a ratio that each corresponding side is a multiple of 1 of the other. And we'll talk about the congruency a little bit later on. But the scale factor would be there. So, to highlight this a little bit more, what if I went and I told you that this angle B down here was 45 and angle E was 45? Okay? Hence, they got the 1 line in there, right? The tick mark. They're congruent then. That red double line, or we'll go to the top. If I told you this was 50, well, that's a bad 50. And I told you D was 50. Again, they have a tick mark, right? That's the same tick mark. What's angle C? Might have to take a calculator out. That's 180 minus 45 minus 50. What's angle C? It'd have to be what? 85? And wait a minute, we can find angle F, which is the other one way over there, using the same logic, subtracting from 180 and find out that's 85 as well. And wait a minute, they are the same, so therefore all the angles are the same. We kind of showed you using numbers instead of just the fact that 2 angles equals all 3 angles. Okay? They add up to 180. There's no other way we can make that happen. Okay? And again, this scale factor, whether I'm talking about the small triangle to the large triangle, so if I'm going in this direction, it's going to be small to large, or S over L. That'll give me a ratio. Or if I'm going in the other direction, I would say it's L over S. We're going to use that in a little bit here. Our goal is to always find the scale factor. And to find a scale factor, you need to find corresponding sides. Every problem I've given to you so far, the triangles have been orientated the same way. That means corresponding angles are either the same bottom left, bottom right, or top. Yes? The problems we're going to do, they're going to be mixed up. They're going to be switched around. So, let's take a look at one of those. Example. Find X and Y. Now, on this particular problem, they actually, don't write, you don't have to circle this. Did it really need to tell us that? Did it need to tell us or show us that with tick marks that those two angles are the same? Or could we have found that out ourselves? We could find that out ourselves because they have to be the same because they are what kind of angles? What's that? Not corresponding. They are congruent, but why? Starts with a V.
Vertex.
Ends in vertical.
Vertical.
They're vertical angles, and vertical angles are the same. Okay? So we could figure that out without having to do this. Now, okay, let's think of this. We have two angles that say they're the same, right? We have another set of angles that say they're the same. So what does that tell us about the other two?
They're the same.
They have to be the same. So guess what I'm going to do? I'm going to put tick marks on there. I'm going to put a tick mark that's different than the other two. Got that? I'm going to erase the circle parts that I put on because I don't want to cloud up the picture here. Now I've set up that these are similar objects. Now my goal is to look for corresponding sides. Now this is the thing. I've got a triangle on the left and I got a triangle on the right. If I start with a triangle on the left on top, I'm going to keep the triangle on the left on top all the time to find the three ratios. There are three corresponding sides. There are three ratios. And all three of those ratios have to be exactly the same. So let's take a look on what that would be. I'm going to start with the left over the right. I'll call this left. Whoops, got to change color. Put a color on it. Left over right. Okay? I'm just using this for naming purposes, which means I'm going to set up L over R. That L over R is the proportion we are using. It's just for letters, or maybe don't put an equal sign. It's just for us to establish that we're not going to change the left over the right. So what if I chose 5? 5 is right here. So that means 5 over what? What's the corresponding side to 5? How did you get 7?
Because you see that the 5 is on the side where you have both of the angles the same.
Okay.
It gives you both of the angles.
I'm going to think of it slightly different than where the angles are the same. I'm going to say, what's the angle that it opens up to? Or what angle opens up to that side? It's the one with the single band, right? So I'm going to go to the other triangle and say, hey, there's the single band. What side is opposite? 7. So we know that it has to be 7. That ratio is equal to another side, 4. 4 is opposite the what one? The band with a small tick mark on it, right? The one tick mark band. Which side in the right has the opposite side of the band with a tick mark? The Y. That ratio is also equal to, the only variable or side left on the left is x over 6. Those are my three ratios, and all three ratios are the same. And now you got to solve for x and y. Mr. Concave, I've never solved a problem with two equal signs. Don't. That's the thing. If all three ratios are the same, can't I just take two of those ratios and set them equal to each other?
Sure.
Here's the thing. I'm always going to use the one that actually gives me the ratio. And the ratio on our problem is 5 to 7. So I'm going to take 5 over 7 is equal to 4 over x, solve for x, and I'm going to take 5 over 7 and equal to x over 6. That's y, sorry.
Yeah.
You are correct. Okay. 4 over y. And 5 over 7 is going to equal the same ratio of x over 6. Now, sometimes these turn out to be nice numbers, sometimes they don't. Not a big deal if it's not. Okay? Leave it as an improper fraction, or leave it as a square root in reduced form. How do I solve two fractions equaling each other? Cross multiply. So, this becomes 5y equals 28. Divide both sides by 5y equals 28 over 5. Leave it, because I can't reduce it. Right? Not that bad. The bottom one, 5 times 6. So it's 30 equals 7x. Oh, divide both sides by 7. I don't think I can reduce that as well because 7 is a prime number, correct? So your answer is 30 over 7 for x, and y is 28 over 5. That's how we use those to our advantage. So find x, y, and z now.
Okay, 2 minutes.
2 minutes. Just get some homework.
So set up the ratios. If I have this, now this problem only gives you one angle. So how do we figure this one out? If I only have one angle, I can't set up similar triangles, so therefore I can't solve it. Oh wait, we talked about this. We said, hey, these two angles right here are the same because they are vertical angles. So I'm going to put a tick mark on there. And if two of the angles are the same, that implies all three are the same. Notice I'm going to place something different on there so I can find its corresponding sides. I'm going to set up the ratios, and you guys can solve it from there. What is one of the ratios? Do we still want to go from left to right, or should we go right to left this time? It doesn't matter. You're correct. It does not matter. Let's still go left to right. I'm fine with that. 7 over 10. Because those are opposite the what angle?
Right angle.
The right angle. Okay. And that is my scale factor. 7 to 10.
8 over y.
Here's a problem. I just heard 8 over y. That is actually going from right over left. We need to keep the left over the right, so it has to be y over 8. Now, maybe instead of writing it as equals again, I'm going to take the known scale factor, and then I'll set that equal to the third side, which is x over z. Oh my goodness. How am I going to do this? Wait a minute. That's a right triangle. And if it's a right triangle, I can use, starts with a P, Pythagorean's theorem to solve for z. So on this triangle right here, make sure that you use a squared plus b squared equals c squared. Okay? The homework is on page 34, 6 through 10 basically is what it comes down to. Have a great day.